I'm going to take just a minute to set up here, but it will pay off in that my speech will actually be shorter. And that's kind of what one of my topics is, putting a little bit of effort in ahead of time and saving yourself a lot of time afterwards. I'm going to talk about the single most under-recognized danger in crypto, upgrading a running protocol. The stakes are massive and mistakes are really easy and the consequences are just bad. So Aave deployed a broken upgrade and locked up $120 million for more than a week. And Aave is the second largest DeFi protocol out there. Last time I checked, it had an 8 billion TLV. Compound did $1 billion a few months earlier, and 3 separate audits, and it was frozen for a week and some. Now, I'm not picking on these 2 projects particularly. They both care about security. They both did a good job communicating afterwards. But safely upgrading a protocol is hard. And repeatedly, we see even good projects do a bad job of this. Now, Lido just did a great job of it. They do everything right. And so to some extent, this is just focusing in on what you can do, just 3 things you can do to make your life so much better and not be stupid. So my name is Daniel von Fange. You might know me from Twitter. I'm the smart contract security guy at Origin Protocol. This is going to sound like shilling here for a second, so in 2 sentences I'll be done, and there's an actual point to it. But we just launched a new product, OETH, a few weeks ago, and currently we're the #2 yield aggregator on DeFi Llama for Ethereum. Our previous DeFi product, which is a couple years old, reached a 296 million TLV. Since I've been doing smart contracts, upgrades and gatekeeping, or security and upgrade gatekeeping, we've done 50 plus upgrades to these 2 protocols with 0 hacks, losses of funds freezes, or dramas. So I spent a lot of time over the last 2 years thinking about upgrades, and I really care about this, and it's so painful to see people repeatedly doing it wrong, which is why I'm standing here today. So what's different about new code versus upgrades? When you write a new protocol, there's just your code. It floats alone, suspended in space. You can read your code and know everything about it and what it does. Auditors can look at it and know everything about it. But when you're upgrading your code, there's your code, and then there's all the stuff that's already there. The state data, the config data for your protocol. There's all the other internal contracts that already exist, and then there's all the external contracts all around. It's this cloud of existing state and contracts that broke both the Aave and the Compound upgrades. In both cases, the new code that was deployed was audited. It was correct in one sense, but it did not fit the environment that it was put into. This is the biggest difference between fresh projects and upgrades. Correct code is enough for new code, but for a safe upgrade, the new code also has to work with everything in the existing world. And one more thing, when you write a new system from scratch, you're often thinking about the entire system as a whole. But when you write an upgrade, you're thinking about less. You're thinking about as little of the current code as you can possibly get away with to write the upgrade. But the reality is when you write an upgrade, you actually need to think about more, not less, because of all the other things that are out there. So I'm going to go over 3 important things you need to do good upgrades. The first one is simple, and that most people here probably know about this one. Raise your hands if you know about this one. All right, good. I've got news for half of you. The #1 rule for upgrades is don't accidentally reuse storage strats in proxied contracts. The consequences can be so bad, so fast, that I'm going to be talking about this one first, even though to some extent it's common knowledge and it's something that auditors are good these days about checking, and a good auditor checking an upgrade will catch this one. So I'm going to move over here and use props for just a second. Testing. Awesome. All right, so everything that your contract stores goes into numbered storage slots. And the variable names in your contract have nothing to do with what's actually going on under the hood in the EVM. So in the EVM, it's just slot 0, slot 1, slot, giant hexadecimal number. And so when you write some code, and we're going to call this one foo here, the compiler just assigns foo to slot 0 here, and then whenever you set foo to 3, it puts those things in there. Hang on just a second. And so now when your code pulls up foo, it reads 3. Same thing, we'll put bar over here. And we'll put one thing in bar. So if you write a new contract and you change the order or somehow switch things around so that the compiler changes which variable names go to which storage slots, when you read foo now, you get the wrong value, not what you were expecting. And let's say one of these was your admin address and the other one was your interest rate or something. If you switch those two, it's really bad. You no longer have an admin and your interest rate is now a bonkers number. So that's the first thing, you've got to read the rules on this one. It's way more complicated than I can actually talk about now, but go read the Solidity website. Hang on just a second. Yeah, so read the Solidity website on how those rules work. That was the demo there. Okay, so that's the first step, is knowing about it. Second step is check it automatically. OpenZeppelin has some good JavaScript tools that will compare your old contract storage to your new contract storage and see if you've changed the name of anything. And so we have that built into our CI pipeline. There's also a library called Foundry Storage Check, which I've not used, but tries to do a similar thing for the Foundry side. But it's important, put it in so that every PR that goes into your continuous integration gets checked, comparing the old contracts to new contracts, and throw a big red mark if you've changed your storage slots. So here's a little bonus secret in between the three things. You want two contrary things when you're doing ongoing smart contract development. You want safety and you want speed. And these are opposed to each other. Safety means taking more time, checking more things, and that's the opposite of speed. So kind of what separates great contract development from good contract development is finding ways to cheat this paradox. And one of the most powerful cheats I've found is to have security critical code as small as possible. If 10% of your code ensures the correct behavior of the other 90%, you can operate much faster when working on the rest of the code. And you can check the correct behavior of the safety code much easier because it's a much smaller set of code. Uniswap v2 is a great example of this. The protocol is split into a safety part, tiny pool contracts that only move money and ensure that the amount of money in them just goes up. And the rest of the complexity is pushed out into the router that makes the system easy to use. But just because the safety checks are in a small place, the router can't mess up the safety of the protocol. So this split between critical and non-critical code is not only a great design for building a protocol, it's also a really good way to upgrade one, because a lot of the contract upgrades can take place in a much less critical manner. And it doesn't have to be in separate contracts. It can just be parts of the same contract or code if you want. All right, so on to the second must-have. Atomic programmatic deploys. Sorry. So many projects build their deployment plans last after they've written their new code. And for some project, maybe there's a text file that says how to deploy it, and eventually maybe something gets put into governance. But let's step back and look at the bigger picture of an upgrade. Most projects have two phases for an upgrade. First, a deployer key creates new contracts, possibly configures them, and then hands ownership over to a governance system of some kind, like a multi-sig or a much fancier community-driven governance system. And so then that second governance system then actually switches the contracts over from the old system to the new system, and may do governance config changes as a part of doing that. So what you really need to do, the right way to do this, is to have all of your stuff about the switch defined in one file. You want to do your deployer actions, do your framework or your governance actions, and then if you're running in a local situation, simulate that governance action taking place and happening. So this also has a benefit that you're testing, you're running your deploy process over and over and over again while even writing the code for your system. And so when it happens for real, it's not a surprise. Everything just works. And you also want your thing to go into effect in a single atomic transaction, everything happening at once. Otherwise, the people get to play with an inconsistent state, which is pretty terrible. I am going to skip that for time reasons and go on to kind of the main reason for this. Fork testing. Fork testing is absolutely amazing. It's the most underutilized tool in smart contract development. And I mean, imagine how powerful it would be if you could take a snapshot of the entire universe, try something new with no consequences, and then come back with what you learned. So forks allow you to have the effect of making a copy of the entire blockchain, deploy contracts, and then run transactions as if you were in a copy of the world. So there's 3 valuable things you can do from a fork. The first is you can just play with your new code in the real environment as if the upgrade had happened. And you can run this, you can run your DApp against your new code, or play with it from Brownie or something else that lets you just play with stuff. There's tremendous value in finding bugs or things you didn't think about, the stupid bugs in that, or just understanding the behavior of the system so you build a gut reaction feel for it. Secondly, you can write tests that run against the forked environment. Just like your unit test, you can make sure that somebody can deposit to your protocol, withdraw from your protocol, that a sensible amount of interest gets earned, and it's testing that on your new code before your new code is ever even live. And just put it in your CI like everything else, and it finds out, every time you push a commit up, it's making sure that you didn't break your existing system. And really, they're not they're like 1 or 2% harder than a unit test to write. It's really easy to do. Lastly, and this is new technology these days, you can actually fuzz against your fork test. And so this is even powerful. You can throw 1 million randomized tests against your fork environment and see if it works or doesn't work. And what's great about this, we heard the question about formal verification. Well, how do you test your interaction with all your dependencies? This tests all your interaction with your dependencies. And so if you were using Aave like we are, or Compound or stuff, you get to find out if your code has some kind of mismatch with their system before it actually goes live. It's kind of amazing. And so Foundry, you can now have these built-in ability to fuzz onto a fork test. And let's see. That's pretty much it. This is the conclusion. Don't be stupid. I'm on Twitter at DanielVF. Thank you.
Okay, it's time to questions. Question for questions. Yeah, I see one. Can you help us with the microphone?
Thank you for the presentation. Might sound as a dumb question, not sure, but so fuzzing seems to only interact with a smart contract on the local environment. How do you emulate the adverse environment that exists on mainnet on your local environment? Is this something that is possible? Is this something that is lacking, or is there a solution?
So let's take Foundry, for example. When it's fuzzing, it's got a local copy of the EVM running. And when you're fork testing, you have a local copy of the EVM running, and when it doesn't know something, it goes off and fetches that information that it doesn't know from the blockchain, loads it in locally, and then uses that from then on. For time reasons, I skipped demoing how forks work, but that's basically a part of how forks work. And so if your fuzzer needs to, hits a code path that talks to Aave, it'll go load in the Aave code. And then if it hits a code path that uses a particular account, it will go load that at or that data from Aave for that account or something. And so it basically just works. It will make a lot of RPC calls, either, I guess, even fuzzing a small amount is still a pretty great idea. Even if you only run 10,000 transactions, that's 10,000 times more than test happened on Compound for that upgrade. But if you really want to honk it, you'd run your own node to point to locally or nearby where you're fuzzing. Next question.
Okay, yes. So another question here.
Just to continue for this fuzzing on mainnet, there are a few things maybe can you advise for the best practices. The first one, in unit test, we can really add some predefined computations to check the function works correctly. For example, just hard code a few numbers, compute them on the paper, and so on. When you use fuzzing, you enforce copy-paste, so you can go to the sum contract, copy this part of the code, put to the test, so you mean that the function which sum 2a and b equals to the result of the same function. So basically, it do not make your system more reliable because you should implement the same algorithm for fuzzing testing if you want to compare the result which you compute independently with the things you have in the same time. And for mainnet, another part is very interesting because primarily we use fuzzing testing to find problems with huge numbers if you have some overflows and so on. When you start on mainnet, you have a pool limit on Compound, for example, 10 millions, it's okay, but it means that if you want to provide greater value for the fuzzing test, there is not enough liquidity. And in this case, could you suggest to really impersonate the Compound, for example, root role to add more liquidity, or what's the best practice to test fuzzing if the existing protocol has very small limits which do not cover the whole range of possible testing? Thank you.
Yeah, those are good questions. So you kind of hit on this at the beginning, but often when you're writing a fuzz test as opposed to a unit test, you kind of want to use relative tests. This account has 1 ETH more than it used to have instead of saying this account has 1 ETH. So you're often diffing it. Secondly, I'm a pragmatic dwarf, and if I can make my life 90% better for a little bit of effort, I would love to do that. And so you don't necessarily, you can do your fuzzing tests where they don't have to be absolutely verified to the single thing what you're actually going to get as a result. If you catch the big things, that's, a lot of times, there's great value. If somebody ends up with a whole lot of money, that's a problem. Or if it just breaks, that's a problem. I forgot your last question in there, so sorry about that. Catch me afterwards.
I want to announce the break, 15 minutes break. Next session would start in 11:30, but I think that we would have time for 1 or 2 extra questions, but let's say thank you to Daniel and give some noise for him.